Missed the first two bullets in the recording, but moving on to the third bullet. We're just trying to make sure, did we get everything? Here's our list of items for course content. These are the things that we need to talk about. We're going to be done with this class soon. We want to make sure if this is what I use as a template to build a final exam, whether that final exam shows up in person that we have to take, or whether the final exam shows up on Canvas. We're imagining a traditional final exam where we've got a blue book and a sheet of problems. What's on that sheet of problems? Problem 1, vectors and vector operations. Problem 2, vector and parametric equations of lines and planes. Bullet 3, dot, cross, and triple products and projections. It's like, oh, dude, when you were writing this list, did you not realize that two lines above you said vector operations? And are these not vector operations? I guess we're just trying to be more specific now. So earlier we talked about the dot product and the cross product. We haven't talked about triple products. So that's a little bit threatening. Fortunately for our heroes, triple product is a couple of different things. And here's our geometric interpretation. It's the cross product and a dot product. So the thing that I didn't say, because it never occurs to me to say this, is that the scalar triple product will be the volume of parallel pipette. You're looking at two vectors, A dot B cross C. So I never really justified this, but it's the volume of the parallel pipette. And then in typical Wikipedia fashion, it says, oh yeah, we could talk about this more. But think about how much I talked about the scalar triple product. Considering I just mentioned it, it's week 15 and vector operations were a long ass time ago. It would be uncool for me to throw onto the final exam a big problem on the scalar triple product. That would be a gotcha question. And I don't play gotcha questions. Does that make sense? Later on, you might be in some class and your physics professor is going to be like, oh, we just need the scalar triple product. And you're just going to nod knowingly. But your internal monologue will be like, oh, Leach, you betrayed us. You were supposed to prepare us for the future. And you didn't. And then I'll receive that psychic message. And I'll send back the telepathic message, dude, I'm not allowed to look into your future. I didn't know this was going to happen to you. And what kind of whack job is going to make you calculate this by hand or something? I don't know. Just kidding. So dot product and cross product, these are things that we talk about. Projections is part of that dot product business. How much of one vector is pushing the other vector along? That's that 50 miles per hour for 5 hours, but not all the 50 miles per hour is going in the direction of 5 hours. I need the component of that 50 miles per hour in the direction of the 5 hours. So I'm going to multiply by the cosine of the angle between those vectors. That's dot product. That's what showed up way later down here. Oh, I got to need to point down here. Way down here in our fundamental theorems of calculus. I like how the course content for a calculus class never even mentions fundamental theorem of calculus. Seems like a big deal. It's like the whole, where this whole arc is headed. That'd be like ending the Lord of the Rings with Sam and Frodo at the door at to Mount Doom. It's like, oh, roll credits. So are you gonna make another movie? It's like, oh no, done. It's like, well, what? That done. So dot and cross products. Can you make the calculation? Can you interpret the results? What do I want out of cross products? Two vectors in R3 define a plane. The cross product will be normal to both vectors. So the cross product of those two vectors in the plane can be used to describe the plane itself. The components of that normal vector will show up as the coefficients in the rectangular equation of the plane in standard form. Those are the things, that's something that I want you to know. Differentiability and differentiation, including partial derivatives. Well, of course, because we're talking about functions of more than one variable. Partial derivatives should just be like where we start. But that's fine. Partial derivatives. Chain rule, higher order derivatives, directional derivatives, and the gradient. We've clicked off all of those boxes. We didn't spend a lot of time on the chain rule, but we have talked about partial derivatives. Our higher order derivatives, remember when we have a function, the mixed second partials are going to be equal. That was important when we got down to things like scalar curl and determining if the function was a gradient field. Directional derivatives. This is where we're just using the dot product and combining it with derivatives. We know that the gradient, which is also right there, should come before directional derivatives. I mean, I don't know who wrote this. The gradient tells you the steepest direction up a curve. We know that it is perpendicular to the contours because the contours say where the function is not changing. Contour is where the function is constant. Gradient is perpendicular to that, and that's the direction of maximum increase. This goes together with what we want to do to find the directional derivative. It's a dot product because the dot product says how much is going in this direction. If we are going in the direction, if we are going perpendicular to the gradient, that is along the contour, then stuff is not changing. And the dot product is the product of the magnitudes times a cosine of 90, which is 0. So it makes sense that when we're perpendicular to the gradient, nothing is changing. So the dot product is telling us how much of that vector, how much of the gradient is going in that direction, or how much of this vector is going in the direction of the gradient. Incidentally, that brings us back to this projection business, dot product. Arc length and curvature, tangent, normal, and binormal vectors. So have I ever said the word binormal before today? Clearly, I'm less concerned about that and more concerned about tangent and normal because of the way that I cast this entire class. So because of the perspective that I like to take on this entire class, which is take Calc 1 and Calc 2 and spread it out to functions of more than one variable, I focused more on tangent and normal than I did to binormal. Binormal is the cross product of the tangent and a normal vector. There you go. Am I going to write a problem on binormal vectors? No, because at this point, that would be a gotcha question, and I don't do gotcha questions. I don't do trick questions. I don't do gotcha questions. Unless it's D&D, in which case it's all just going to be trick questions. So there's that. But never come at your students with trick questions when actual points are on the line. Vector valued functions, those are the vector fields that we've talked about a lot. They're derivatives and integrals. The del operator, integrals, fundamental theorem of calculus, finding velocity and acceleration. You have a position, its derivative, the derivative is velocity, the derivative of velocity is acceleration. That's an old idea. We just have vectors attached to it now. Remember, a vector says can denote a position, then the derivative will be tangent to that position curve, and that will tell you your velocity, just like it always has. Rad. Real valued functions of several variables, that's where we open. Level curves and surfaces, that's where we open this class with. We took functions of one variable and just said functions of two variables now. Instead of one-dimensional curves in R2, we have two-dimensional surfaces in R3. Those are our functions. Limits, continuity, and properties of limits of continuity. I didn't really talk in great detail about justifying that I didn't justify that we could take all those ideas that are applied to functions of one variable and now apply them to functions of two variables. This was like that last section in chapter 12 where I skipped really try to justify limits in continuity. Mostly because we had bigger things to fry. Because in week 14, I want to be talking about the fundamental theorem of calculus. And that requires some rigor to get kind of like, it works the same. So you can just trust us on that. So that was good. Number 8, not really a question worthy. Local and global maxima and minima. Extrema, I think that's excessive. You could have just said local and global extrema. Here's one of the things that happens when you try to make a document that's built to justify other schools accepting some other Calc 3 class. So like you're going to transfer to some other school to get a degree in engineering because we don't offer bachelor's degrees in engineering. So you're going to have to transfer, go to another school, and they're going to want to know what'd you do in Calc 3. And honestly, the answer across the country is we did Calc 3 shit. What do you think? And really the question is, did you do vector calculus and multivariable calculus? And you'd be like, oh yeah. And they just need a document that says that. And so you end up with a document like this. Someone wrote global extrema and then just went on with it. Or they wrote global maxima and minima and then just went on with it. But then the problem is we've gotten to a point, and this is at this point in your mathematical career, not a lot of people know as much math as you do. Think about how shaky you are feeling about your Calc 3 knowledge. You are still like in the top 10% globally of mathematical knowledge. Just no one does this. This is borderline wizardry. You come along and start doing this kind of stuff, you do it in the wrong place. People might like burn you at the stake. It's like, well, what is this witchcraft? They're like, oh, it's calculus. And they'll be like, oh, you know what that sounds like? Another word for witchcraft. Step this way. So then what happens is like the articulation officer has to be familiar with all these things, which is an unfair thing to ask. They're like, oh, well, I don't see global extrema on this list. And like, oh, dude, we said maxima and minima. And then the articulation officers are going, listen, motherfucker, I am not trained in calculus. I said my math department said we need to talk about global extrema, and you talk about global maxima and minima. I just got to say, hey, there's a discrepancy. And so we go back and we throw that in there. You know what I mean? We've had an articulation problem with Calc 2 at one point with, I can't remember which school it was, because we didn't use the specific word transcendental functions. Because in our hubris, we just listed the different transcendental functions we talked about. You know what functions I'm talking about. You know what transcendental functions I'm talking about, right? What transcendental functions are you familiar with? None is incorrect. You just didn't have them called transcendental functions. So it's really uncool of us to be surprised when we get a message that say, you didn't list transcendental functions. And then you look at your list of exponential, logarithmic, trigonometric, inverse trigonometric. It's like, oh, we listed the ones that we talk about. So then that tells us to go back and say transcendental functions such as, and then put our list in. Do you know what I mean? Because here in a room full of students that are supposedly well-versed in Calc 3 that I'm about to pass in Calc 3 and then send them off into higher level maths, I'm like, oh, what transcendental functions are you familiar with? And you're like, oh, none. I've never heard of that. You know what I mean? So it's uncool to ask that of an articulation officer. It's like, I'm just trying to match stuff up. Because they're just like shaking their heads like, oh, fucking academics, man. I don't know your jargon. That should be like the first line of every email, the subject line. Articulation problem. I don't know your jargon, asshole. So anyway. Saddle points and Lagrange multipliers. Lagrange multipliers is just a constrained optimization problems. We had a few problems in that section. Vector fields. I'm like, well, didn't you talk about vector valued functions? That's fine. That's fine. That's fine. Vector fields, including the gradient vector and conservative fields. We talked about conservative fields. That came up a couple weeks ago. Awesome. Double and triple integrals over a region, over a solid. What's x between? What's y between? What's z between? We even did that stuff in cylindrical coordinates and spherical coordinates. All right, applications of multiple integration, such as area, volume, center of mass, and moments of inertia. I don't think I did a center of mass problem. It's an average. You're just trying to find the average. Where's the middle? If there's a bunch of mass on one end of the rod and not so much mass on the other end of the rod, you want to find where the center of mass is. You just got to find where half the stuff is, right? More variables. Change of variables theorem. Did I phrase it that way? Not sure. We'll come back to that one. Integrals of real valued functions over surfaces. Dude, 2 spaces up, you just said double and triple integrals. Line and surface integrals, including parametrically defined surfaces. And I think we found the last thing that I need to talk about. We've talked about defining curves parametrically, right? And that was critical because we couldn't do that with a function anymore. In R2, if I write y as a function of x, I am writing a curve in R2. If I write down a relationship in an equation with x and y, I'm defining a curve in R2. But in R3, if I write an equation involving x, y, and z, or a function where z is a function of x and y, or the other way around, x is a function of y and z, where one variable is a function of the other 2 variables, we're defining an entire surface. And in R3, we might be integrating over a curve, a one-dimensional curve. So we did parametrically define curves in R3, but we did not parametrically define surfaces in R3. We got to find out if that's going to produce anything interesting. Integrals of real valued functions over surfaces. Oh, that's actually literally the same one as 14. That might be on me. I'm gonna have to check my source on that one. If not, I don't know if I'll send an email or if I'll just make fun of them here. Because it's not like it's a critical change, you know what I mean? Like if like points were on the line that this thing was listed twice, then you probably should raise a stink. If someone's going to get arrested because this thing appears twice, then someone needs to say something. But I might just use it as a vehicle to make fun of committees writing lists. Divergence and curl. I did just kind of tangentially hit divergence and curl. I want you thinking about it still. And our fundamental theorems of calculus and things that are fundamental theorem of calculus adjacent, Green's theorem, Stokes' theorem, divergence theorem, and the fundamental theorem of calculus for line integrals, which is a strange omission from this list of course content for a Calc 3 class. This only seems like a lot that we've covered because it's a lot that we've covered. And we've talked about it in great detail. What I want you to do now is imagine what this would look like. Pick any one of these things and think, what would this look like as some kind of problem on an exam? Let's pretend that we're sitting down in a room with a blue book and a list of problems, even though that's not going to be our format. What would it look like? How is Leach going to ask us about vectors and vector operations? What is he going to ask us? What tricks are we going to be asked to perform? Vector addition, scalar multiplication, dot product, cross product. Then are we going to be called upon to interpret those things? What double and triple integrals are we going to be called upon to calculate? We did spend a lot of time setting up double and triple integrals in both directions, dx, dy, and dy, dx. So we emphasized more the setting up of the integrals and less the calculation of the integrals. So what kind of problems are we going to have there? What did those problems look like? Let's see. Line and surface integrals. What kind of questions could arise around line and surface integrals? Will we be called upon to parameterize a curve and calculate a line integral? One sneaky way that this problem shows up is that I actually calculate a line integral over a gradient field, but I don't tell you that it's a gradient field. I like telling you that that's a problem that shows up in Calc 3 style finals, because the question is about, did you check to see that this is a gradient field? Did you check to see that you could use the fundamental theorem of calculus for line integrals? The reason I kind of like waver on that one is that it kind of feels like a gotcha question when you don't tell the students that it's a gradient field. They're like, oh, did you check it's a gradient field? And they're like, well, no, I just calculated the line integral. Ho, you could have just done the fundamental theorem of calculus. And they're like, well, thanks for telling me now, asshole, after I did all that work. You know what I mean? Because I don't know that that's an important distinction. But then it kind of ruins the question. If I say, here's a gradient field, calculate this line integral. At which point, I just remember, it's this question of, do you remember the fundamental theorem of calculus for line integrals? And if the answer is no, and you just kind of brute force it again, I'm like, oh, I tried to tell you. You know what I mean? It's really hard to draw a line of what I'm expecting you to know. And that's why I really struggle with what problems to write. It's like on a final exam. Should it make a difference between an A and a B or a C? Should it make a difference in a student passing or not passing an algebra class if they just forgot how to factor the difference of cubes? Anybody here tell me how to factor the difference of cubes? X cubed minus Y cubed. How does that factor? Seems like a fucked up question to put on your final exam if it's going to be enough points to cause a student to not pass. If you are going to fail a student and you can point to, and they're missing 4 points, and if they had only remembered to factor the difference of cubes, then they would have passed. You really got to wonder if that should be there or not. Does that make sense? Considering I just asked a room full of Calc 3 students who are about to pass Calc 3. And I'm pretty confident if I put that on a quiz right now on a piece of paper and handed it to you and I said no phones, most of you would not get it. I'm just talking about straight up X cubed minus Y cubed, factor it using the difference of squares, the difference of cubes formula, not some kind of obscure way where I give you the quadratic portion of this and I say rationalize, right? Here's the cube root of X squared minus the cube root of, plus the cube root of X, plus the cube root of XY, and then plus the cube root of Y squared, and say rationalize this cube thing, right? Not some kind of obscure way, just a direct question. Factor this polynomial with the formula. I don't know if we remember. You know what I mean? I think there might be only one person in the room that remembered those. And that is probably because they spent a long time teaching algebra. You know what I mean? Very difficult to come up with these kind of questions. So this is your job. This is what I want you thinking about. I know I want you thinking about all the time fundamental theorem of calculus, vectors, and derivatives, and all this shit. But now we need to start thinking about practical things. There's only 3 weeks of classes left before finals week. December 9th is the last day of class. December 9 plus 7 is going to be the last day of finals week. That's when everything has to be done. If you send me an email on December 9 plus 8, it's not going to get a response until January, at which point it will be too late. Does that make sense? Obviously depends on the nature of the email. But if it's just like, oh, Leach, I kind of messed up and I didn't do this stuff, can I get an extension? you won't hear back from me until like February. And my response will be like, well, next time when you're taking Calc 3 again, don't do that. You know what I mean? But when I get the email that says, I just got out of the hospital, then I might show somebody. Maybe. Incidentally, if it just occurs to you, it's like, oh, I didn't do stuff, I'll just tell Leach that I was in the hospital. You're just a shitty person. I mean, that's just the thing. Probably because you're living in a shitty system where teachers demand things like doctor's notes and shit like that. So I admit that as a society, we have ruined people. We've made people bad, but don't do that. Fix the problem now. Since I'm telling you that it's going to be a problem, fix it now. Any questions? Think about what should be on a Calc 3 final, not just in general, but specifically for this class. Think about, try to figure out what kind of problems I seem to give a shit about. Because those are the kind of problems I want to say, can you do this? And you're going to want to be able to say, yeah. So tell me what those problems are. Any questions? All right, it's week 15. It's time to think about the meta. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.